All right, I'm going to try and do an example of each of the 4 types of problems that students are having the most difficulty with. So I'm going to start with the first problem on page 12 of the learning target practice sheets. This is drawing models to solve problems involving ratios. So the first problem, in a box of candy, the ratio of cherry candies to lemon candies is 4:9. So first I want to make sure I understand what I'm finding the ratio for. So cherry candies to lemon candies is 4:9. So I'm going to start by drawing a bar diagram to help me with this. This means for every 4 cherry candies, there's 9 lemon candies, or I can think of it as 4 units of cherry candies for 9 units of lemon candies. So I'm going to draw a bar diagram with 4 units and label that C. That represents my cherry candy. And then my lemon candy, I'm going to draw a bar that has 9 units. And what is important to understand when you're using bar diagrams is that each unit on both bars represents the same number of items. So each of these units could represent 1 candy, in which case you'd have 4 cherry candies and 9 lemon candies, or each of these units could represent 2 candies, so you'd have 8 cherry candies and 18 lemon candies, or each unit could represent 3 candies, so you'd have 12 cherry candies and 27 lemon candies. So it's important to remember that each of these units represents the same quantity or amount of whatever it is being considered. So we have our ratio of 4:9. Now it tells us if there are 45 lemon candies in the box, how many cherry candies are there? So now we're being told that these 9 units of lemon candies represent 45 pieces of candy. So I want to use that information to figure out how many candies there are per unit. Well, if I have 9 units of lemon candy and 45 candies, then I can figure out how many candies are in each unit by doing 45 divided by 9. So my answer is 5. That means each of these units represents 5 candies. And then as we stated, each unit in both bars represents the same amount. So that means each of these units in the bar representing cherry candies is also equal to 5 candies. So that means I have 4 times 5, or 20 cherry candies. And that's it. Okay, let's move to the first problem on Learning Target 13. On this page, you're being asked to solve ratio problems that involve 3-part ratios, and they're really no different than ratio problems involving 2-part ratios. You can still draw a bar diagram. It can still be really helpful. So let's look at our first problem. The ratio of the number of orange trees to the number of apple trees to the number of pear trees in an orchard is 5:3:2. If there are 750 trees in the orchard, how many of each type of fruit trees are there? So again, I'm going to start by drawing a bar diagram to represent each item. I've got orange trees, and those are in a ratio of 5 units. To apple trees, and those we're going to represent with a bar of 3 units because it's 5:3. And then lastly, pear trees, and that bar is just going to have 2 units. And again, it's important to remember that even though I didn't draw these particularly equal looking. Each of these units represents the same number of trees. So then the information they give me is that there are 750 trees total. So I don't know how much each bar equals or how much any one bar equals, but I do know that altogether they represent 750 trees. Now, again, if each of these units represents the same number of trees, I could total them up. Let's see, there's 5 plus 3 plus 2, that's 10 units. So these 10 units represent 750 trees. So if 10 units equals 750 trees, then 1 unit must be equal to 750 divided by 10, or 75 trees. Well, now I know how many trees are represented by each unit. And that lets me figure out how many there are of each kind of tree. Pear trees are 2 units, so 2 times 75 is 150 pear trees. Apple trees, there's 3 units. 3 times 75 is 225, so there's 225 apple trees. And oranges are 5 units and 75 trees per unit, so 5 times 75 is 375 orange trees. Right, so that's solving a ratio problem with 3 parts using a bar diagram. Okay, so let's move to the first problem on the Target 14 page. I can draw models to solve problems involving 2 sets of ratios. All right, so our first problem, in a school, the ratio of the number of girls to the number of boys is 4 to 5. That's one ratio. Now we have a completely different ratio giving the number of boys to the number of teachers, and that's 15 to 2. Then it states there are 144 girls in the school. How many boys and teachers are there? So when we do this, we have 2 different ratios. We've got 3 different items or types of items. We've got girls, boys, and teachers. And the first ratio we have is girls to boys, which is 4 to 5. And then the second ratio we have is boys to teachers. It has to go on a different line because it's a completely different ratio, which is 15 to 2. Now our goal here is to take these 2 different ratios, since they have an overlapping type of item, which is boys. We can take these 2 different ratios and combine them to make one 3-part ratio. So we look at the term, the item that both ratios have in common, which is boys. So in order to turn this into just one 3-part ratio, I need to reconcile these 2 terms. I can do that because I know how to find equivalent ratios to a given ratio. So what I want to do is look at these 2 terms, 5 and 15, and think, what could I multiply one or both ratios by so that these 2 terms, 5 and 15, are equivalent? Well, 5 is a factor of 15. I know that if I multiply 5 by 3, I can get 15. But the rules for finding equivalent ratios tell me if I multiply one term by 3, to keep the ratio equivalent, I have to multiply the other term by 3. So I'm going to go ahead and do that. Now, 5 times 3 equals 15, And then the first term for girls, 4 times 3 equals 12. Now I've changed my first ratio into 12 and 15. And my second ratio is 15 to 2. Now these overlapping terms for boys are the same, and I can write it as a single 3-part ratio, 12 to 15 to 2. Now it's just a 3-part ratio, and I can use this information to help me find how many boys and teachers there are. The problem tells me that there are 144 girls. But in my ratio, girls are represented by 12 units. So if 12 units is equal to 144 girls, then 1 unit is equal to 144 divided by 12, or 12 girls. All right, so now I know how many students or teachers there are per unit. So if there's 15 units of boys, 15 times 12, let's see, 12 times 10 is 120, 12 times 5 is 60, so that's 180. So there's 180 boys, and 2 units of teachers means there's 24 teachers. And that's that. All right, let's try our last and arguably the most challenging type of ratio problem, which we call before and after ratio problems. You're given an initial ratio, the quantity of one of the items changes, and then you're given a resulting ratio. So let's just dive right in. Our problem here is that the ratio of the number of pencils to the number of sharpeners in a box was 1 to 2. So I'm going to label this pencils, sharpeners, and my ratio was 1 to 2. Then it says 9 more pencils were added. So when I add 9 pencils, the ratio becomes 5 to 4. And the question is, how many pencils and how many sharpeners were there in the box at first? All right, so when I look at these two ratios, I have two quantities, pencils and sharpeners. One of the quantities changed. The number of pencils changed. But one of the items didn't change in quantity, and that was sharpeners. So the first thing I do when I approach solving these is know which of the two items didn't change quantity. The sharpeners didn't change quantity. So just like before, when we had the two sets of ratios that we wanted to make into a single 3-part ratio, I want to reconcile the two terms for sharpeners in the before and after ratio. Because the quantity didn't change, so if I can make these constant, make the numbers for the sharpeners constant, it allows me to make a valid comparison for the number of pencils, or the number of units in pencils. So 2 is a factor of 4. If I multiply 2 by 2, I get 4. But again, in this first ratio, I always have to keep them equivalent. So if I'm going to multiply the number for sharpeners by 2, I've got to multiply the number of pencils by 2 as well. So all I'm doing is writing an equivalent ratio. I'm taking this first ratio, 1 to 2, and rewriting it as an equivalent ratio of 2 to 4. Now that I have reconciled the two terms for sharpeners, it allows me to make a comparison of the change in units of pencils. My number of units of sharpeners now is the same, 4 and 4, and that makes sense because it didn't change quantity. But my number of pencils, initial number of units was 2, the end number of units was 5. So what happened is I added from 2 to 5, 3 units of pencils. That means my 9 pencils must be equal to 3 units. So if 3 units equals 9 pencils, then 1 unit must equal 9 divided by 3, or 3 pencils. So now I should understand that each unit in these ratios represents 3 items. That means when I started, I had 4 units of sharpeners. So 4 times 3 sharpeners per unit is 12 sharpeners. And the question was, how many pencils and sharpeners were there in the box at first? Well, the number of sharpeners didn't change, but if we want to look at how many pencils were in the box at first, there were 2 units. So 2 times 3, or 6 pencils to start with. And then we can always go back and check our answer to see if it makes sense in the problem. We're saying there were 6 unit pencils and 12 sharpeners to start with. Does that make sense in a ratio of 1 to 2, 6 to 12? Yes, it does. Then 9 pencils were added, so those 6 pencils were added to 9, became 15. And the ratio became 15 to 4. So then it was 15 pencils to 12 sharpeners. Is that a ratio of 5 to 4? Yes. So it checks.